So this is a paper published by the researchers from Southeast University in China, where they assembled the reactor design from different parts of the world, from the different papers, and then they discussed it. So I have kept this paper in the Dropbox because I didn't find it necessary to copy and paste from here into the PowerPoint. So this is one design that which is a moving bed design adopted by the Ohio State University, and this is the moving bed. Okay, and then the air reactor is here, combustor. It's a very simple arrangement, very clever arrangement, and works quite well for their type of coal. Let me go one step back first to revive your memory. What's a fluidized bed regime? Fluidized bed regimes mean? Professor Shah did mention about all of this. The bubbling bed is here, where the actual velocity is just over the UMF. Then you have the spouted fluidized bed, which is the sort of fluidized bed that I was referring to. There is a spout tube through which very high velocity jet goes, and then with the expectation that it will be creating a vigorously fluidized zone. And then you have the circulating fluidized bed, which we are mentioning. Is the actual velocity is much higher than the minimum fluidization velocities. Just to give you an example, for 100 micron particles, the minimum fluidization velocity will be 0.02 or something like that, meters per second. So in the bubbling mode, you supply anywhere between 0.2 to 0.6, 0.7, 0.8 meter per second, so it's more than 10 times. In the circulating fluidized bed, you are supplying 3 meters per second upwards, 3 to 5 meters per second velocity. So it is much higher than the minimum fluidization velocity of 0.01, 0.02, etc. meters per second. So let's look at this a little bit more, because the fixed bed or the reducer is really the key. So they have the solid fuel going here, and then it devolatilizes. The char goes this way, the volatiles go that way, reacts with the incoming iron oxide in a countercurrent mode. So it's a very clever design, and it works very well for their coal. The coal doesn't undergo significant attrition or significant fragmentation at all. So that's the Ohio State University's design. Their initial one, but since it's a 25 kilowatt thermal, but since then they have built a larger one as well. And the air reactor, as you can see, the bottom part is very large, simply to accommodate all the materials that are coming from the back or from the bottom end of the moving bed reducer here. So this zone is larger in diameter, this zone is smaller in diameter. The larger diameter allows more of a bubbling kind of environment, so that the oxygen carrier gets sufficient time there to oxidize, and then it just is carried away from here at high velocity and through the cyclone goes in here. So this is, so char that is not burnt, let's not worry about it. That for the time being, we are looking only at the 2 reactors configuration there. Moving bed reactors provide a very long residence time, and if you have significantly long residence time, it's very unlikely that you will actually be getting much of a char left. Correct. Fixed bed or moving bed, whatever you call it, because the iron oxide particles, they fall from the top as the volatiles go up. So that's their design, and it's their unique design. Why isn't it coming? Oh, sorry, say again. Okay. Sometimes it works, sometimes it doesn't. Okay, so it has gone to the next page. And this is the design that was first adopted at Chalmers University. On the left side, the fuel reactor and the air reactor, as you can see, the air reactor is very similar. The fuel reactor actually has a loop seal. Loop seal means the oxygen carrier from here has to drop here, then go up. Of course, they haven't shown the fluidization gas, etc. in here, and then they will, as they build up, they will then drop here. And then internally, they have a somewhat very clever arrangement that the metal oxides, once they get oxidized, they get separated in the cyclone, the gas goes that way, and then the metal oxides fall here and then go build up, and then come here and fall into the fuel reactor. Then the Spanish did it slightly different, CSIC, the figure number 7 on the right hand side. Essentially, the air reactor is no different, but the fuel reactor is slightly different, as you can see. This is actually the fuel reactor. It's a small facility, 500 watt thermal. So 1000 watt is 1 kilowatt, 500 is half a kilowatt. So they could do it this way. So what happens is the coal is fed from here. It's very standard design screw feeder, and the metal oxide is loaded prior to the experiment, or they can, if they want to, but I don't think they do it. If they want to, they can also feed it through the coal conveyor. Then they have these so-called loop seal arrangements. So here all the fuel reaction with the metal oxide takes place, and then the metal oxides, and they also have the steam connection there at the bottom, steam as well as nitrogen. So whenever they want, they can put in steam. When they don't need, particularly at the beginning, they start doing it only with nitrogen. Okay. So there, the metal oxide then falls from the overflow of the fuel reactor, goes to a second loop seal, so that it falls, and then in the second loop seal it builds up, and then it grows, and then it comes to the air reactor. So loop seals and external heat exchangers do play a very important part in the fluid beds design and operation. It ensures that the flow is only in one direction, that the flow is not solids flow, gas flow, etc., is not from the other direction. And the fluidization air, as I showed previously, really does ensure that. Okay. So these are These are very well known in the fluidization community, and those who have done some amount of fluidization work, they will know how to design this, or how much and what frequency to purge the fluidization purge gases, so that the pressure drop is only, the pressure loop balance is maintained very, very well. So that's the Spanish one. It has been, both of these rigs have been extensively used. I have seen the Chalmers one in operation, and it's a brilliant, simple design. So, Mighty 5. Takes some effort to go from one page to the other. I don't know why. Expert. Good. Okay. So this is a IFP in France. As you can see, quite complicated. The actual thing is, it's a 10 kilowatt thermal, and they show the the metal oxide, the fuel reactor on the left, and I have never tried to actually understand this much, to be honest. Some papers have come through it, few papers, but majority of the papers have come, that have been published, have come from the Chalmers group, the Ohio University group, and the Southeast Chinese group, in that particular order. So this group I have never seen much coming, real work. So this actually does corroborate one of the messages that I am trying to give is, there is no point trying to build a very fancy looking complicated one. Keep it simple, so that you who will be the operating, your life will be simpler. So let's go to page down. This is at the Hamburg University of Technology, 25 kilowatt thermal in Germany, and here you see the air reactor on the left is a very tall vessel, 8 meters for 25 kilowatt, and then you have the fluidized, the fuel reactor, and the coal and the gas is sent through here, and they have the provision to put in water vapor and carbon dioxide to convert the unconverted char. And so what actually happens in here is that it is essentially a two-stage bubbling bed with fluidization velocity as written. It's only about 0.25, and the air reactor with the fluidization internal diameter of the fuel reactor being 250 millimeter, height 4 meter, whereas the air reactor has only 100 millimeter diameter and 8 meter height, and fluidization velocity is very, very high. So why the fluidization velocity is much higher in the air reactor than in the fuel reactor is that you have to bring the oxygen carrier back quickly from the air reactor to the fuel reactor. So that's why you need the higher velocity. Of course, you provide the residence time, longer residence time, through the taller height of the air reactor. So the point that I'm trying to make is that, and we'll see a few others as we go forward, but let's take a step back and then discuss this. There are a whole lot of designs that you can do that, in the laboratory. It doesn't have to be a design that you think should match with the commercial plant that you are going to build or have in mind. Maybe, maybe not. If it doesn't, not to worry. Important thing is to design a reactor for laboratory application is to ensure that it is simple, it can be operated, but most importantly, that it creates the same temperature and hydrodynamics condition as you would expect. For that, you don't need to match the shape. For that, you only have to match the flows and the temperatures. Similarity in the flows and the temperatures. So we all know what similarity laws are. So that's the most important thing. Otherwise, do it in your own design, keep it simple so that you can operate it. Ensure that it reaches the temperature that you want it to reach, or the temperature at which you want to get the data, and the hydrodynamic condition, particularly the velocities, that is similar. There is absolutely no reason to match the flow field completely with the commercial scale one, because no one will know what the flow field in the commercial scale one will be. So you can do your CFD predictions, CFD calculations to find out what's the flow field look like, how the flow field looks like in your reactor, but that's as much as you will go. Trying to perfect that is a folly, not necessary. Ensuring temperature, ensuring velocity, most important, nothing else. So the next one then. This is the second unit at the Spanish, where they moved away from 25 to 50 kilowatt thermal, and so they have two similar looking fuel reactors, the blue one on the right and the red one on the left. And you can see the solid circulation measurement devices. As I was talking about yesterday, which someone asked me the question, how you measure the solid circulation rate? Remember? Who was asking it? Yeah. So I said that you actually put a valve, flap a valve. So normally it will be open. So during the measurement solid circulation rate, so you have another one in here. During the solid circulation rate measurement, you close it for 1 minute, everything will be accumulated on top of it, then stop the fluidization air, collect it. That's what they are doing. And then you can say that in 1 minute I have collected this much. You have, if you can do it safely, do it for another time. Repeat it a few times so that you can get a good feel. So that's from the measurement side, but then you can also calculate it from the pressure loop balance, that the pressure drop across a certain length, known length, is always proportional to the flow across it. So you should be able to, there are formulas available for that, so you can match whether they are the same or not. But whatever you do, I suggest that this sort of measurements be carried out in a safe manner, so that you are no longer relying on what actually the formulas are predicting. You can show a comparison, but that's as far as it. So coming back to that again, here they have the carbon stripper. I think by that time, in the initial design, they didn't have carbon stripper. They realized that that would be necessary. but in the smaller rigs, often once it is built, you are not able to do much modifications. Either the space won't allow, total space, or the spaces in between the two are so restricted that it may not be, you are much better off to build a new one, taking into account all the experience that you gathered. So they built this one with, and of course the first one did not have the facility to measure the solid circulation rate. So they have the carbon stripper here, otherwise this very standard loop seal arrangement, in both sides. And in the carbon stripper, I draw your attention to the introduction of steam. So in the carbon stripper, you can try to react the carbon with either steam or carbon dioxide or both, but keep the provision if you want to build, but use only one at a time. That's much better. So, you can use nitrogen, you can use carbon dioxide at best, nothing other than that. Nothing other than the, maybe, but you know, it's much better to, they have kept the provision for both nitrogen and air, as I can see. So it depends on what you, what they use. So keeping a provision is one thing, and then you would ideally think that you would be better off to use the nitrogen rather than air. Yeah. I think you can. If it serves your purpose, there is no reason why you can't do it. That's the point I make. There is no hard and fast rule. Use whatever you want to use to ensure that you are achieving your objective in a simple manner. Putting only oxygen, the trouble is temperature can run away. And then you will be solving another problem which you have created. It's like, you know, nothing to do, so mix some rice with dal and then lentil and then separate them one by one. So why create the problem? Solve it. Keep it simple. And you will know all these things. Okay. But you see the feeding system, screw feeder, 50 kilowatt thermal, they will be easily, they will be using about, I would say about 5 kilograms per hour. Screw feeders work quite well for those sort of feed rates, quite well. The other thing to note in the figure, description of the figure, is the height of the reactors, the fluidization velocities in the fuel reactor as well as in the fuel reactor. Air reactor is always higher. Then the next one is in China. China, they have many universities have rigs of their own, everyone. So Huazhong University of Technology back in Wuhan, this is a 5 kilowatt thermal rig that they made, continuous. I'm not sure how long it has worked, anybody's guess. Fuel reactor circulating bed internal diameter is only just over 2 inches, 55 millimeters, so tiny. And the air reactor is 45 millimeter. Height is 550 millimeter. And the rise at internal is 22, which means here it is 45, here it is 22, half of that. This sort of small reactors, small diameter reactors are very difficult to operate consistently. Half an hour, 1 hour maybe, okay, but other than that. So you have to apply your judgment when it comes to the results from different rigs. Then based on that 5 kilowatt thermal one, Huazhong University of Technology, they went on to build a larger one. This is 50 kilowatt thermal, and but I don't see any details of it in here, but obviously the diameters will be an order of magnitude higher. So Southeast University on the left side, the design, as you can see, is more or less similar to the Chalmers one. As far as the fuel reactor and the air reactor is concerned, with the one difference, and everyone wants to be a bit different, is that from the fuel reactor, the bed materials are supposed to go through this passage and then fall in there. So one of my students went there, spent few months, and couple of months actually. They have published quite a lot from in here, and one of their students, one student came and worked with me in our reactor for 1 year and went back with all the experimental data. And so again, if I had the option, I wouldn't do it that way. I would not do it this way. I would do it in the standard loop seal arrangement, which knows to work. Then you also have the right, on the right side. On the left side one is 10 kilowatt thermal, and the right side, this is 1 kilowatt thermal, but everything is inside a furnace. The rationale, inside a furnace. So the heat is provided. Okay, so let me go one step back now. The larger the rig, better it is to control the temperature. I mean, most possibly it will self-control. Thermal inertia, smaller rigs, as a proportion of the heat input, heat loss is much, much higher. So that's why for the smaller one, 1 kilowatt thermal, they have put everything inside the furnace. So my rule of thumb is that even for our 10 kilowatt thermal, we initially have to heat it up with hot air, and then once we start coal feed, and the coal ignites and releases the heat, then it becomes self-sustaining, and then we wind back the furnace heating. We have heating at the bottom part of our reactor, not the entire one. 10 kilowatt thermal. Yeah. So 10 kilowatt thermal is something that you can handle quite easily. It has a footprint of about, everything included, analytical instruments, gas analyzers, etc., about 3 meters by 2 meters. Footprint. Height is another aspect. Everything is 4 meters, but we have a high bay, so we could go up to 6 meters, so if necessary. But I wouldn't build anything less than that, because otherwise you'll have to supply heat all the time. So 1 kilowatt thermal, no wonder they have put everything inside a furnace. Some countries have a lot of money. Some countries have a lot of money, so they can update it regularly. Some countries have less money, which therefore they want to design it in such a way that you don't spend updating it regularly. But many universities have their own rig, simply because it's the human psychology. You have one toy, I want another toy. He wants another toy. everyone wants to talk. Anyway, that's a different philosophical discussion. We don't need to go into it, right? And then the cold model of the fluid CLC reactor is good that Lai Hong's student has sent it, and Lai Hong's student is coming to work with me next year. She is still waiting to get her visa for almost 9 months now. Anyway, so Lai Hong Shen is the professor there, very well known in the CLC literature. But yesterday, everyone saw the cold model, right? So the cold model is really, really needed because it tells you so many things, and particularly the loop seal arrangement and the operation of the loop seal. No matter how many times I tell it to you by showing it from a figure, until such time you see it once, you won't appreciate it in full. It has to come from out. There is no other alternative. So I always tell everyone that please build a cold model, preferably one-to-one. In the universities you can do it. It doesn't take much here. And as long as you avoid the dust explosion thing, dust explosion, that's a completely different area, you are fine. So never allow static electric charge to be built. So I think you should push some copper strips around that, ground it. Otherwise, the static charge can build up very, very quickly, and then you go near it, push, you'll get a big shock. So copper strips are quite cheap. You can just build it and then connect it through the rig. This side as well as that side, so that the charge gets dissipated. No one writes about it. But anyway, so this is the cold model. And then the next one is in the Vienna University and Technology CLC facility. It's a very well designed and very well operated rig. And look at the simplicity of it. So the fuel reactor and the air reactors are separated, but they have this facility which is they can operate it either as a gasifier or as a continuous chemical looping gasifier mode or chemical looping combustion mode. I mean, you can do that, and that's what they have written in here. But it was predominantly done for gaseous fuel. And I don't, to my knowledge, I haven't seen them going into the coal mode, because in Austria there is not much coal research going on anyway. They're all natural gas. But the important thing is that we have been talking about chemical looping in relation to solid fuel coal or biomass, but the research actually started, and Austrians were one of the front runners. Research actually started with natural gas based research. Natural gas is also a hydrocarbon fuel, so is coal. And then the Darmstadt one. This was built with Alstom's money in Darmstadt in Germany. We had a tie-up with them for quite a number of periods. Even now we talk regularly. Our student went there, and they have advised us a fair lot. But it's a 1 megawatt thermal unit. It's a very large unit, and they have carbon stripper, as you can see, in between the two. So the air reactor is on the left side. It doesn't show all the details, but the important thing is that I am not exactly sure why the fuel reactor diameter is smaller than the diameter of the air reactor. Maybe there is a reason for it, that never divulged it. So that's the red box surrounds the fuel reactor. That's what is shown, and coal is fed in from the by gravity feed, and from the cyclone, then it goes to a loop seal, and loop seal is fed with nitrogen. As you can see, loop seal is fed with nitrogen, and then it goes to the carbon stripper, and from the carbon stripper then it goes to the metal oxide, then goes to the air. And but they have in the loop seal connected to the air reactor, they obviously can have air. That's not a problem. So, and they have the ID fan separate for this unit, separate for that unit. I am actually not sure. Okay, let's go one step back. Why their diameter of the fuel reactor is larger than the air reactor, why the height of the fuel reactor is larger, I'm not sure compared to the air reactor. Maybe they deliberately build it to check a whole variety of fuel, but never it was made clear. But everyone has, as you can see, everyone has steam and carbon dioxide injection, and here they have the propane injection facility to heat it up. Okay, and so also they have the propane injection facility for startup purposes. Similar to the commercial rig, you will be heating up the reactors with natural gas, and progressively then once the temperature higher than the ignition temperature of the fuel is reached, then you will wind back the gas and then pull the coal in, and that will then get it going. No, I think it's not the standard method. It's just the provision that they have kept, because in the pilot plants you can imagine that maintaining the pressure balance in 3 different reactors, interconnected reactors, with so many cyclones. So there are 3 cyclones, there are 3 reactors, there are 4 loop cells. So I guess they put the screw conveyor for metal reactors, metal oxides to be fed back into the fuel reactor purely for the sake of simplicity, nothing else, so that you can get it running and then generate the information that you want, even though in reality it may not resemble what it will be in the commercial unit. Why? Because it is next to the propane. So propane, you have to burn the propane, right? Otherwise, and then send the flue gas. So you need air. Only during start, for sure. For sure. Okay, so I think what is happening here is that if for some reason they see the temperature is running away for whatever reason, just douse everything with nitrogen. Do we require? In the carbon stripper, as I said, this is a provision that has been kept. If for some reason there is a fire there inside, so that the temperature is so high, then you need that provision. So there are in the large pilot plants, actually you build so much redundancy, so much flexibility. The purpose is to make this thing run so that you can get the information that you want. Okay. So, that is why you keep provision for it. It is not going to cost you significantly higher level of money, but at least it will give you the peace of mind and the flexibility to operate. That is it. Okay. Yeah. So, what you said, I agree 1500%. It's good to see that all of your understandings after such a crash course is improving. So you all are much smarter than I thought, much smarter than I was at your age anyway, which is good. That's the generational thing, I think. Some people talk less, but they are very smart. Okay, so then the Chalmers University then went into build from the 25 kilowatt thermal to the 100 kilowatt thermal unit. So that's how it goes. If you have a long established research, you learn so many things, and they honestly speaking in Europe they are the front runners, and in US Ohio State University the front runner. Two completely different types of fluidization battery arrangement, and everyone else is doing catch up. Just seeing what these two are doing and then just learning from them. So this is the schematic and the CAD drawing, I suppose, on the right, and but the gasification arrangement in the for the char to be converted is steam. That is what they have written, but the dimensions are all given. I think this more like 100 kilowatt thermal is quite a big unit for a university to handle, and you can see I think it's about 5 meters tall, right? Yeah, 5 meter. So including all the superstructure, etc., you are easily looking at about 7 meters from the ground to the top. So it's a substantial unit. Again, it has I would say that it has been also built with a fair bit of flexibility. On that side is a fuel on the right side is the fuel reactor, and on your left side is the air reactor. But they have published enormously from this ones, and which I saw it only once, and they could make it work. And the larger the rig, usually better is the control. Then Alstom themselves built a 3 megawatt thermal unit. So the Darmstadt had 1 megawatt thermal. Alstom they had their own 3 megawatt thermal unit, and that's the largest that has been built so far. I'm just trying to see where it is. So they again, this is not necessarily what will be there in a commercial plant. Still a fair bit of flexibility is built in, particularly if you look on the left side, the main seal pot and the fluidization legs, the diplex means the downcomer just below the pipe below the cyclone, on which all the solids fall into the external heat exchanger, which is called the main seal pot. or the primary and the secondary cyclones. They have two levels of cyclones, so that not much is missed. So, if you look at the dimension of it, it's about 70 feet. So, 70 feet is what, about 3.2 divided by 3.28, about 23, right, or 22 meters. So, it's a fairly tall structure, but this is quite common. And then Southeast University then went on to build, apart from their 5 kilowatt thermal unit, which they built another one, this time for doing chemical looping on sewage sludge. So that's why their design is different. If you can recall now, actually they have introduced a proper loop seal kind of arrangement between the two, rather than that on the side inside the fuel reactor there was a vertical line, vertical section through which the metals were, this char and metal oxide was forced to flow. Possibly that didn't work, not surprising. So that's why it is like that. And the 2 kilowatt thermal one, again built for solid fuels, built for sludge, but everything inside the furnace. So you can see their thought process. They had 1 kilowatt and 5 kilowatt thermal unit for coal. Then they have 2 kilowatt and 5 kilowatt thermal units separately for sludge. So if you have money, you can build. This one I am not sure where it was built. The one on the bottom. It's a generic design. And then the another 50 kilowatt thermal unit at the CSIC in Spain, with the internals somewhat different. It shows on the left side the internals, the reactor section below the ring and reactor section above the ring, how they connect. So it's the overall height is 4 meter, but it's not a single piece, single pipe of 4 meter tall. It's made up of different sections, and the in between the different sections, what they have is they have the different wedge shaped rings. So it's one section here, one section there, and in between they have this. If you can see it as projected, it's an hourglass kind of arrangement. I think they have given a reason for it. They just wanted to have larger velocity in that section, going from one section to the other, eventually leading to the cyclone, even though the velocities will eventually be recovered at this part. But at least through that one it is forced. What benefit it brings to them, that they can tell. What else do I want to tell? Nothing really. And then carbon stripper. The concept of carbon stripper was actually developed by the Chalmers University, Anders Lingefeld's group. So there are various designs of the carbon stripper that has been floated since they first started it. So let's not look at the left side one, which is a bit more description and details of the different sections of the 5 kilowatt thermal unit for coal at Southeast University in China. But here the carbon stripper on the right side, that's what is shown. As I said, the concept first came from the Chalmers, the Swedish group, and then everyone quickly followed by the IFP in France and Tsinghua University in China, which is but I mean, in essence, it connects to a loop cell with the solid oxygen carrier from the fuel reactor, and then through another loop cell through the air reactor. So there are essentially two loop cells here. One is just after the cyclone, returning the metal oxides into the fuel reactor, and then there is another loop cell in here, so that it reacts. It doesn't allow the carbon or the char to go back into the air reactor. This loop cell here is also fluidized with steam, so steam gasification can occur. But what they haven't shown in here is the effect of the fluidization gas, which can carry forward any char either there or together with the metal oxide here to be converted with the steam. Well, the idea is to remove it completely. So if you give it sufficient time, steam will take care of all the char. So that's not a problem. Correct. So what else did I want to tell? Okay, so this is the most important message. The carbon stripper is generally fluidized by steam and stroke or CO2. So steam is the choice, and if you also have carbon dioxide there, you can use it, but steam is the first choice. In industrial operation, of course, it is preferable to use CO2 to fluidize the reactor, simply because there are plenty of CO2 available in industrial scale. And then here is the carbon stripper. So if you look at the fuel, this is at the Chalmers University. If you look at where is the carbon stripper? The fuel reactor itself actually shows a slightly different internal arrangement compared to the other ones. The fuel reactors, this is the fuel reactor's front view, and this is the fuel reactor's top view. So from the top view, you can see that the materials can go in here and then come to here, and this is what precisely our CSIRO counterparts in their continuous looping reactor that they designed and built, but we could not operate it very long. That's what they adopted from this group's Chalmers' work. But important thing is, in the fuel reactor, every effort is made. Every effort is made to give the fuel very, very long time, so that it goes in here, it falls, and then goes in here, so it gets a fair bit of residence time together with the oxygen carrier, and then it gets even more residence time together with the oxygen carrier before falling here and then eventually going out. So it's a fair bit of design that has gone on to increase the residence time. The purpose is to increase the residence time. I would never think that this is the configuration that would be adopted in a large rig if it is ever built. Again, they did it for flexibility's sake in the laboratory, but that's how it is. And it can do it because it's only 10 kilowatt thermal reactor. What else? So this is by far, this is all that I wanted to show to you. The other one, hang on. So there is a little bit more. This is a computer generated thing. Remember I was talking about the distributors, and I drew this thing in the bubble caps, and these are the bubble caps. They literally look like that. So from the bottom, there are several jets coming in from one single source, but so that the tops are protected, they have this particular arrangement. You will get to see that in many fluidization book, Kunyan, Levenspiel, etc. But it was first started at Cambridge and at University of British Columbia, John Grace and Paul Watkinson. They are the ones who actually made these things, all sorts of designs which almost universally now is adopted by everyone. And then also, so this is a carbon stripper design for the 100 kilowatt thermal CLC reactor in Chalmers University, and there the fluidization gas is provided. The combustion gas is provided, either steam or CO2, provided from the bottom, and they have whole lot of baffles, which is shown a little bit more details in here, but the one that is adopted at the IFP in France, their design is slightly different. The gas goes from the top and then is channelized through a jet through the central pipe, and everything, all the combustion that takes place in here. The carbon stripping takes place in there. So there is no hard and fast rule really for separate different entities. They do it differently with the purpose of getting. There is another one at Chinese university, Tsinghua University. Their design is different, as you can see from the left-hand side in here. Again, I believe this is a cold model photograph that they have shown. I don't remember having seen that 5-6 years ago when I visited, but maybe it has been, when it's 2015, so certainly when I went there, it wasn't there. Then they also have their own concept of riser-based carbon stripper for the coal-fueled CLC reactor, and so these are two interconnected ones. One is a bubbling bed, and with another fluidized bed in here with this interconnection. I don't think much is actually known in here. How it operates is anybody's guess. I haven't read that particular paper, so I wouldn't be knowing. But you can get the some of the references in this particular paper to get more information if they provide on their rigs. But it's all different people do it differently, and with the sole aim of generating information from a rig that they think can be operated. Okay, so that's basically it for the reactor part. I would now go back to the go back to the my PowerPoint presentation. We'll finish around 1:15. Going to the PowerPoint presentation. So this is where we moved to the PDF paper, PDF version of the paper. So now what we are saying is, so far it was all the discussions were focused on coal combustion. Chemical looping. So it was chemical looping combustion, CLC. But the principle of chemical looping can be extended to many other applications. And that's what we'll be showing now. So one is chemical looping air separation, which we briefly mentioned. Then we also, when we were discussing hot gas cleanup 2 or 3 days ago, maybe Friday, right? I did mention that the regeneration of the solvents for the gas cleanup essentially follows the looping principle. And you can actually think of, if you are working in that area, can think of labeling your work or directing your work more towards the chemical looping arrangement for gas cleanup, because that will be something new, something novel, and potentially very useful to all that is needed for a PhD work. It has to be new. There has to be a novelty factor, number 2, and that you have been able to go into the depth of it mechanistically rather than shallow and breadth of work. So you can consider that. But the point I'm trying to make also is that chemical looping is a gold mine area to work for PhD, or for that matter masters as well. And there are more than just coal combustion or biomass combustion or coal gasification or biomass gasification that you can study using the chemical looping one. So if you are early in your PhD work just doing the coursework, then you may try to brainwash your supervisor to let you work in that area. If he wants to be washed. I often get brainwashed. I'm very supportive of the students. If they come up with ideas and if I can provide the money, then it's fine. 16. Only. No, all you have to do is to tell them to come up with their thoughts. You must be seeing that every time someone asks me a question, I don't answer. I simply deflect the question back, either from that direction to that direction, depending on the angle of incidence, or and that's how you get the discussions going, foster discussion, and through which we collectively learn. There is no need to think that your supervisor knows everything in the world. No. Supervisor is just a guide. Will be telling you that don't go to that path. If you want to go from here to there, you may decide that I will go this way, or I'll go this way, or I'll go that way. And if your supervisor sees that you are going too much tangentially in the other direction, his or her responsibility is to bring you back. But the supervisor's responsibility is never to tell you how to do it, because then you will not become independent researcher. You have to become independent, because at the end of the PhD, you will be expected to supervise. So in as much as I can tell, okay, what can be done, but that will not be your PhD. Then it will be partly my PhD. So by all means, argue with your supervisor politely and in an articulated manner. That will be very good. But not every one of us can take criticism because we are humans. You have to give the PhD students, you have to think that the PhD students are actually, from a supervisor's perspective, they are actually your colleague, not their undergraduate or school students. They have their knowledge base. You have to respect it. You have to respect others to earn respect. Otherwise, it never works. And allow them to learn at their own pace. This is the most important thing. But if you see that a lot of students are working too much time on Facebook and YouTube, etc., during normal hours, then obviously you can tell very frankly that, look, please don't do it now. Do it at other times. You need to do that, but not all the time. So that's why we see that those who complete in 3.5 years, and there are many, they actually can do quite well. And it can be done. These days, you can get hold of a paper at 2:30 in the morning from your bed, because everything is electronic. Back in our time, we had to rush to the library when the library told us that a fresh, a certain issue of the journal has arrived. Then you had to go and flick through the pages and photocopy and come back. Now, every day, every night, you get all this automated things, so you can be productive. The most important thing is this is your life. I'm telling it to this PhD student. This is your life. This is part of your work, but this is not entire part of your life. Get the work done, get a good work done, and get out. Get out of the university to practice your art. That's what you will be doing, because the time that you spend here at the university, you will never get it back. You will never get it back. This is also the most exciting time in a young person's career. And you have to enjoy every facets of life. PhD is not the only thing. So the thing is, be productive. That's why I said, I wrote in that book, work smart. It's very important that you work smart, then you can be productive. And always ask the question, but if you ask the question, always be prepared to provide an answer as well. Then collectively as a supervisor-student team, or the supervisor and the group as a whole can answer it. So that's why in our group meetings, everyone presents sometime majority of the students give only a 2 or 3 minute updates of their weekly progress, and one student or two students give a half-an-hour presentation, but then everyone then listens and then give comments on the spot, which tells two things, which helps the student who is presenting, but also it helps the students who are commenting. Because the ability to hear from someone on a completely new topic, a topic other than your own, digest it, form some opinion, and then ask the question is an art that you all have to learn. When you go to the industry to work, that's what the industry will be expecting of you, because they will be paying you some real dollars, real money, and they want return. No excuse to run under the umbrella of a PhD student anymore. So that's why, in as much as you may dislike me, that's why I tell you, please talk, please present. Until such time you write or you present or do both, you actually don't know what is wrong in your argument. And you have to learn it fast, very fast, now or never. Okay, that's enough. Sorry, that's a bit of a pep talk, nothing else. So there are different ways of applying the chemical looping concept. Why? Okay. So one is, we did mention about it, that chemical looping is essentially also is an air separation process, if you look at it that way, because what comes out from the air reactor is the oxygen depleted air, right? So essentially it's more of a concentrating the nitrogen, provided you are able to accomplish it. So that's what it is. And the University of Newcastle in Australia, they worked a fair bit on the class principle, chemical looping air separation, and they did it first on a very, very small scale. Then they went on to slightly larger, and then a very large unit was built together with all the process simulation, CFD simulation for the two different reactors, and the life cycle analysis has all been carried out. I had the opportunity to independently review the final report last month on behalf of their government who funded the university work. So there are still a few unknown issues, but let's take you to the principle of it. That's what this course is all about. So you still have the two reactors, fuel and the air reactor, if I may say so, and the hot air comes in here, and then a hot reduced air goes in, and the metal oxide obviously goes back. So it's just to get the heat balance correct, so that everything that has been generated, the heat that has been generated in the air reactor, which is an exothermic process that goes on, is essentially utilized through the heat carried by the oxidized metal oxide going into the fuel reactor. That's what the key is. So establishing the solid circulation rate, establishing the getting rid of the carbon from the process, in the process generating steam if it is possible, but getting oxygen or getting the nitrogen out is really the key. In principle, the class works, as you would expect, works much better for natural gas, gaseous fuel, I mean, because there you won't have the problem of carbon, unconverted carbon, as you would have in biomass or coal, etc. So this is a fair bit of work. There is a fair bit of work that has gone on. I have taken this figure from their publication back in 2010, so almost 10 years ago now, but a considerable improvement have been made in other places. But as I see the recent reports, the technical reports, I think there is still a fair bit of work to be done to fine-tune the type of oxygen carriers that you will be able to use in here. You will not be able to use the very fine particles of oxygen carriers, unfortunately. So let's not go too much into it, but I thought it will also be useful to copy this particular graph from there, which shows the type of oxygen carrier that they found reasonable to use, which is a mix of manganese and cobalt. Both these are known to give up their oxygen rather easily compared to iron oxide, but they are expensive. But for class operation, if you are because you are class operation with natural gas, because you don't need any interaction with solid fuel, the cost aspect will be not all that critical. So this graph in here, it shows the conversion time and average conversion rate of the oxidation of a 1-to-1 mixture of the manganese and cobalt metal oxide system. That's what it shows, that in around 675 Celsius you get good conversion, and that the time for 95% conversion is only less than 2 minutes. So the rather than reading too much details from it, because if you want to fully identify and fully appreciate the work, you will have to read the full paper. The message that I would like you to take somewhat at a macro level is that, number one, plus is good for natural gas. Number two, cost of the metal oxides is not not that critical as it is critical in a coal direct chemical looping, coal-based or biomass-based looping. And this sort of research can tell you whether it will take a very long time or reasonable time to do the air separation. Okay. But potentially this could be a game changer if it can be made to work compared to the cryogenic air separation unit. And the beauty of it is that it actually produces the air almost at ambient condition or at a higher temperature, depending on how much heat you are extracting. So the other point that we'd like also to make here is that if this is for air separation, which means it is giving you oxygen and also it is giving you nitrogen, then potentially there is a retrofitting opportunity for retrofitting means a power station exists and then you add few things onto it. That's what retrofit is, not a wholesale change. So if you want a power station, for example, working on air CFBC, if you want to convert it to oxygen-fired CFBC, then you can either go into that direction or you can actually have into the direction that we already discussed this morning and yesterday, normal CLC application, or you can have a separation unit based on class principle, not cryogenic principle, and bring the oxygen that way. So opens up another thought process. Then this is the one that our IITB student Sonal Thingani did, and Sonal is now at MIT. So he got his PhD and did all the work at Monash and went back and did all the calculations with me and Andrew Hordley and Sanjay. And then he now is doing quite well. So this is an alternative process for nitric oxide and hydrogen production. And where it is useful is for nitric acid production, for example, you need a fair bit of, this is the conventional process. So what is you do is you have natural gas steam, you do the conventional steam method deforming. So that's almost 100 years old technology at 10 bar 750 that gives you hydrogen. Then you bring in nitrogen from somewhere and then run it at Haber's conventional Haber process to generate ammonia in 1:3 ratio of hydrogen and ammonia to nitrogen. And then you use the Oswald process, again is more than 100 years old technology, with platinum catalyst and 10 atmosphere, 900 degrees, with bring in oxygen. That produces nitrogen, and that then with steam and oxygen goes on to producing nitric oxide. So there is the industry partner who which is based in Australia but also has a significant presence in this country. They looked at, they funded this work looking at alternative processes for nitrogen oxide and hydrogen production. So what Sonal did was very simple. He looked at the ammonia looping, so all sorts of metal oxides here that we have also screened for coal purposes, but this one is for gaseous ammonia. And then see which one gives how much nitrogen and what are the corresponding. So these are very theoretical calculations, Gibbs free energy calculation, nothing other than that. and then what is the Gibbs free energy, and from there identify some of the metal oxides which are candidates for more detailed investigation. So he then, after this initial thermodynamics work, he then went on to carry out the experiments. So it is the ammonia looping, as I said before. So we have a very simple quartz reactor that was built with a distributor here, which is a sinter plate. It's all gaseous fuel, so both ammonia and nitrogen was fed through two mass flow controllers. So very well characterized. And then the gas eventually went into the quartz reactor. The entire reactor was kept inside the furnace, so that the temperature inside the reactor could be very well monitored and maintained. So there, what he did was, at the other end in the gas analyzer, continuous gas analyzer, he started the evolution, looking at the evolution of the nitrogen oxide and hydrogen production, because these are the two gases that you will eventually need for for nitric acid production. So apparently simple, but not so simple experiments. Essentially, he looked at, by using different types of oxygen carriers here, and different types of oxygen carriers that he selected from his thermodynamics calculations to be the cobalt oxide, copper oxide, and also iron oxide, which are in here, to see what level and when does he sees the breakthrough of hydrogen, when does he see the breakthrough of nitrogen. So simple experiments, but many experiments, and these are easy to be done at different temperatures. So he developed his matrix, test matrix, which we then collectively, Andrew and I and Sonal, we then decided that this will be the test that he should do first. There is a box design of tests, experimental tests. Those who do experiments, you just kind of don't do experiments by bringing in conditions out of thin air. It has to be something called the box design, right? So that if you are there, you identify, okay, these are my variables, these are my conditions, so therefore this is how we will do, and then you put softwares are these days available, but it's simple Excel-based calculations that you can do to arrive at a test matrix, and then from there you decide, okay, I will do this one first, this one first, this one first, this one first. You do initially, you do the screening test, and then those which gives you the best results, then you go into reproducing them. So without going into any more details, what he found was that under certain conditions, ammonia can be reduced to significant amount of either this way or that way. Significant amount of nitric acid or significant amount of hydrogen, and well before we could publish it, the industry participant decided to patent it. So then we went to publish it. So that's not a problem. But because it's a PhD work, he also had to go and do the mechanistic reaction mechanism work. In reaction mechanism, for those who are mechanical engineers, what I say is that you can go from one reactant to a particular product. So just to give you an example, C plus O2 can give you CO2. So on a broad sense, that's the boundary. C and O2 are going in, and eventually you are getting CO2. But the path has not been just a straight one. There has been a different path in between, that you have formed the CO radicals, you have formed the other nascent species, the intermediate species, which then have done the reactions in the gas phase to give you eventual product. And so what you can do is, you can actually propose a mechanism that this might be my way, and then test it through experimental work and with the help of fast analysis, you test whether that is really the path it has taken or not, so that the radicals and the intermediates that that he was proposing, whether that any existence of those ones were found or not. If not, find another mechanism. So that's what mechanism work is all about for any product, whether it's biofuels or, for that matter, any gaseous products coming from coal gasification or biomass gasification. You can have that mechanism based work. And for CLC, there is an enormous CLC. I mean, there is an enormous opportunity to do the reaction mechanism work, and that itself can be 70% of a PhD. So PhD is not necessarily all about building a large rig and then carrying out experiments there, but it could be just as simple as such a small rig, well controlled, setting it up, designing it, setting it up, and doing the experiments with many repeats. That's where the philosophical contribution eventually comes, with the final pinnacle being the mechanism work. So that was his own path that we convinced him to take, and he put the effort, and then it's a fantastic piece of work. So that paper is there. If you get the time, please have a casual read. And so when you do the thermodynamics calculation, you essentially look at what the Gibbs free energy is. Right? So if one has a very large negative value and the another one has a very small negative value, which one you think will be more favorable path? Everyone agrees? There you go. That's the starting point. That's the starting point. Problem arises is if that information is not available to do the calculations, then you will have to think it a different way. But for majority of the cases, thermodynamic data are available now. So you do the for any looping work, whether it is looping combustion or looping gasification or looping these sort of things, your starting point will be the Gibbs free energy calculation. Simple thing to do, but it's a solid foundation through which you are basing your next step. Okay. And then, of course, you have to make a decision. If there are 2 or 3 of them are the same values, then you have to make a conscious decision. Okay, my next level of decision is based on economics. If just hypothetical sake, if platinum gave you a very large negative value, you would say that if there is something else which is cheaper and closer to it, but slightly less, I will go for it. But platinum catalysts are used. Yeah. So thermodynamics is the starting point. Thermodynamics doesn't tell anything about kinetics. That's what you will be doing through the experiments. But thermodynamics is the starting point. Always. You cannot beat thermodynamics with any catalyst. Catalyst can only catalyze it fast, but catalysts won't be able to take you, as far as the product composition is concerned, beyond the what's predicted by thermodynamics. Okay, so then the next one is the urea production. Urea, as you know, just 5 more minutes and then we'll be off. The conventional process, urea is a fertilizer. Okay. So the way it works is you have the natural gas reforming, so steam reforming, as simple as that. Then you have the CO2 coming from somewhere. CO2 can come from a power station after being absorbed or being captured by an amine unit, or from a CL unit if you like, but we'll see that. And then you have the methanation, then you have the cryogenic distillation column, and eventually you produce the ammonia, and then ammonia, and the CO2 gives you the ammonium carbonate, which is the fertilizer called urea. Okay, so that is then what do you do? I don't know whether I have copied. Here. Okay, so that's the conventional process. But then you can think can I see the application of chemical looping in there? So let's see that this is what has been proposed by this particular group, Idrisi et al. That now you have natural gas, so that's a fuel reactor, and then you have a steam reactor. It's a three. This is the Cl group, if I may say so, chemical looping group. So what they are doing is you are eliminating, the CO2 separation and methanation, blah blah blah, etc. And then from in here, because the looping can produce nitrogen, similar to the discussion that we are making, that it is the oxygen depleted air that the Cl can produce. So nitrogen can come from there, and the hydrogen can come from the triple reactor concept that we mentioned yesterday afternoon in the first slide. Hey, next time you come with a bottle of water, you get dehydrated very quickly. I can see from your eyes. Okay, not good. The afternoon is an exciting session. Come with a bottle of water all the time. In this climate, you need a bottle of water. It's good. Anyway, so the point I'm making is just apply the concept that chemical looping, we said, can produce nitrogen. Chemical looping, we said, can produce hydrogen. These are the two ingredients for ammonia. So that's basically it. I don't even need to go into the details of it. So what the people have been doing is when they're seeing that this is a concept that has some degree of merit, and particularly if the looping is based on the gases, it becomes so much easier. So that's what this is. So you produce the nitrogen, you produce the hydrogen. So this is a concept. Of course, this is not the experimental work, but someone has patented it. You can work on it, but you will never be able to earn money by building a plant on it. So that's one. I think we'll stop at this point, and then we will have 3 or 4 more things on different types immediately after lunch, and then we will go to the CO2 hydrogenation. And then for tomorrow morning, then we'll only be having the discussions on the fuel cell, carbon fuel cell a little bit, and then we will all go home. And you don't have to